Okay, so now we're ready for nuclear magnetic resonance spectroscopy. This is the same diagram that we had at the beginning of the IR, and it's got energy going and increasing, and we've got radio waves, microwaves, all the different types of electromagnetic radiation. Before, we were looking at rotational motion and molecular vibrations. We're looking at these molecular vibrations, and that gave us the IR diagrams we were looking at previously. Now we're going to be looking in the radio range, and we're going to be looking at nuclear spin transitions. So NMR is used to determine the structure of compounds by studying the interactions between electromagnetic radiation and the nuclei of atoms. A nucleus with an odd number of protons or an odd number of neutrons, and in this case the ones we're going to be interested in are hydrogen and carbon-13, has a nuclear spin. When the nuclei is subject to a strong magnetic field, it aligns itself with that field. So here we are with no magnetic field, and here we are with an applied magnetic field. You'll notice that some of the nuclei here have lined up with the field. This alpha here has lined up with the field, and this one has with the field, but some of them are against the field. So this beta is against the field, and this one is against the field. Okay? There's an energy difference between being in the alpha state with the field and being in the beta state without the field. So this is the supposed energy of the alpha spin state, and this is the energy of the beta spin state up here. And when the proton transitions from the alpha state to the beta state, it uses this amount of energy. This amount of energy is usually in the radio region of the electromagnetic spectrum. Each nucleus is affected by the electrons around it, so the energy gap between the alpha and beta states differs for each atom and will appear as a separate peak. So acquiring a spectrum. First, you need a very strong magnetic field. They usually do these super cold for that reason, to establish the required energy gap between the spin states. And then we need a source of radio frequency. The magnitude of this gap, the delta E, is going to be dependent on the strength of the magnetic field. In general, we make a very strong magnetic field by passing a current through a superconducting loop of material that is very, 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 very cold, very close to absolute zero. So our magnetic fields have to be very strong. To prepare the sample, has to be dissolved in something that doesn't have any protons, because that's what we're looking at is proton spin. So we're going to dissolve in a compound without protons. And you're probably already asking, that's got to be pretty hard, right? Well, we can use carbon tetrachloride, or we can use a deuterium form of water. This is where deuterium has replaced hydrogen. Deuterium also has spin, but it absorbs in a different place, and so it doesn't cause a problem.